So this section is on projectile motion, with linear air resistance. Recall this is for v small velocities and small diameters. And so as we approach a lot of problems, we just start with Newton's second law, and we say the sum of the forces is equal to the mass times the acceleration, right? And in this case, this is the force of gravity, right, plus the force of drag is equal to the mass times the acceleration. And the force of gravity is minus mg k hat. If our coordinate system has z up, right, this would be x, y, and z. And so the force of gravity is minus mg k hat, and then the drag force is minus m gamma, nope, try again, gamma v, where gamma is a measure of the drag. And so this always points down the k-axis. Notice this one points opposite the direction of the velocity, and so the v just points, whatever direction velocity is going, your drag force points in the opposite direction. That's what that minus sign does. And so we can write this as, if we go back to this equation, we can write m d squared r over dt squared is equal to, so that's ma is equal to minus mg k hat, that's the gravitational force, and then we say minus m gamma x dot I hat minus m gamma y dot j hat minus m gamma z dot k hat. And so the left-hand side of that becomes m d squared x dt squared, which maybe I'll just write as m x double dot I hat plus m y double dot j hat plus m z double dot k hat equals minus mg k hat minus m gamma x dot I hat minus m gamma y dot j hat minus m gamma z dot k hat. That's a lot. And now I can just split them all up into x, y, and z components, right? And this gives me, and cancel all the m's. Notice I can just go through each one of these guys and get rid of an m. Has to happen all of them. And so this gives me x double dot is equal to minus gamma x dot. Right, I get the x double dot, I get this piece and this piece with the minus sign, and I drop the I hat. This is my I hat direction motion. This gives me y double dot equals minus gamma y dot, and this is z double dot is minus gamma z dot. Like that. Also, minus g. Right. From this term. And so the z term gets the z double dot k hat, and then a minus g k hat, and a minus gamma z dot k hat. And so it looks like that. This leaves us with, well, all right, so I'll erase this and solve. So I can write the x component of that as x double dot equals minus gamma x dot, or I can just say a sub x is equal to minus gamma v sub x. Those say the same thing, right? And so this is just ex dot dt equals minus gamma x dot. And then to solve, I separate variables, and so I say dx dot over x dot is equal to minus gamma dt. And then I can integrate both sides. I can integrate there because that gamma is just a constant for drag, and that goes from 0 to t. And I'm going to say this goes from x dot naught to x dot. Again, x dot is just v sub x, and x dot naught is just v naught x. You can write those however you want. It's a little easier maybe this way, I'm not so sure. And so I can integrate those. This integrates to a log function, and so I can say log of x dot over x dot naught. And I should probably put primes on these ones that I'm integrating, right? If this is the log of that minus the log of that, and so it's just the log of the ratio. It looks like that. It's equal to minus gamma t, right? That's how that one integrates. And that gives us x dot over x dot naught is equal to e to the minus gamma t. And that gives us that x dot is equal to x dot naught e to the minus gamma t. As long as, if we just look at this piece of it, right, as long as gamma and t are both positive, which they are, we're using positive times and positive gamma, this has a value that looks like this, 1 when t is 0, so this is t and 0, and it steadily decreases after that. And so x dot, its initial value is, this is 1, so this initial value is x naught at t equals 0, and then it steadily decreases from there. And that's what we expect for a drag force that's got no other forces acting. The wind resistance is slowly bringing the object to a stop. Hopefully I don't have to do all this again for the y. Again, the y double dot, if I just write this equation down, if I do all the same things and change the x's to y's, I get y dot is equal to y dot naught e to the minus gamma t, and it has the same equation of motion in the y as it does in x. This is just the horizontal motion under drag resistance. It's like if you had something sliding around on a frictionless surface and the only thing that was bringing it to a stop was air. Of course, this is the linear air resistance, and so it's really only effective for very small velocities and very small diameters, but we can just set that aside a little bit while we're just talking about it. So now we need to do the same thing for z. It's a little different because gravity is also acting in the z direction. So we can write our equation that we had earlier, z double dot equals minus gamma z dot minus g, where g is just the constant gravity. Again, this is all in the x direction. I can rewrite z double dot as dz dt, and then I can say, I can divide both sides by minus gamma, and I get minus 1 over gamma. Gamma is equal to, times dz dot dt equals z dot plus g over gamma. And then I can separate variables on this, and I'm just going to carry that minus 1 over gamma along, and then I'm going to say, I'm going to divide both sides by this piece. And so I'm going to say dz dot, and I'm going to multiply it by dt, both sides by dt. And so I'm going to get dz dot over z dot plus g over gamma is equal to dt. And now I want to integrate these things from z naught dot to z dot, and from 0 to t. And so this just gives me a log function. And so the left-hand side is minus 1 over gamma. Looks like an 8. to gamma, right, times the log of, and again, I should probably put primes on my integrating variables inside the integrand, z dot plus g over gamma, divided by, evaluated here, z dot naught plus g over gamma is equal to t. I multiply both sides by minus gamma and raise e to both sides, and I get z dot plus g over gamma divided by z dot naught plus g over gamma is equal to minus gamma t, and this gives me z dot plus g over gamma is equal to z dot naught plus g over gamma, e to the minus gamma t. Hopefully you can follow that, and I'll take that to the next screen here in a second. So I've rewritten the last equation for z here, and now I've just rearranged it. If I move this guy to the other side, I have two terms with g over gamma. One is multiplying e to the minus gamma, and the other one is just subtracted, so it becomes g over gamma e to the minus gamma t minus 1. And then this term just multiplies e to the minus gamma t. And so I can say at t equals 0, if I stick in a t equals 0 here, z dot is just equal to, so this at t equals 0, this term becomes 1, and so I just get z dot naught. That's the initial z velocity. That's good. This term is 1, so it just gives me that. And at t equals 0 here, this term becomes 1, 1 minus 1 is 0, and so I just get z equals z dot naught, which is what I expect to get. And now let's look at t equals infinity, right, or maybe as t approaches infinity, say, right, this is a z dot equals terminal velocity. In z, right? I'm not worried about the x and the y now, and so I can just say, look, the sum of the forces in the z direction is equal to the mass times the acceleration in the z direction. But that's just going to be 0 because I'm at terminal velocity. I've waited a long time, and the drag force is now equal to the gravitational force. And so then I can say, oops, I wrote this wrong. I should say the sum of the forces in the z direction, right? And so what are the forces in the z direction? It's minus gamma m z dot, that's my drag force, minus mg. Those are the z direction forces. I could put k hats on them, but I've already specified I'm just looking at z, and so it doesn't make any difference, equals 0. This just gives me minus gamma z dot, I can cancel the m's, minus g equals 0. This gives me minus gamma z dot is equal to g, or z dot is equal to minus g over gamma, right, as t approaches infinity. Well, if I come back up to this equation here, this is my equation for my z motion, then my z at t equals infinity, this is 0, because gamma and t are both positive, so it's 1 over e to the infinity, which is just 0. This term goes away. And then so does this term, and I just get z equals minus g over gamma, which is exactly what I get, what I expect to get based on the terminal velocity. So this expression, which gives me the equation of motion in z, appears to correctly reflect the initial and final conditions of the motion of the object. So these are the equations for the velocity of a particle with linear drag, right? X, Y, and Z. We've already derived all of these. And so, so they should look familiar already. And so now I want to find the position. And so I'll just start with this one, and it'll do both of these at the same time. We just switch the variables. And so this gives me dx dt, right, is equal to x dot naught e to the minus gamma t. And so that tells me that dx over e to the minus sorry, x times e, sorry, dx is equal to x dot naught e to the minus gamma t dt. I just cross multiplied the d. I got a little excited there, right? And then I can just integrate these two guys. This is x naught to x, and this is, I've got to put my integral there. The x dot naught is my initial velocity. That's a constant. This goes from 0 to t, right? And so the left-hand side of this becomes x minus x naught. That's the change in x position, right? That's kind of what I'm after. It's equal to, I'm going to keep this x dot naught out front, and then I'm going to multiply. So the integral of this thing, I'll just put the 0 to t here again. It's the evaluation at 0 to t of e to the minus gamma t over minus gamma, because that's how this function integrates, right? And so this is x dot naught times that evaluated at t, so it's minus 1 over gamma times e to the minus gamma t, and then evaluate this thing at 0, minus 1. And so x minus x naught is equal to minus x dot naught over gamma times e to the minus gamma t minus 1, or it's equal to x dot naught over gamma times 1 minus e to the minus gamma t. That gives x equals x naught, I'm just moving the x naught to the other side, plus x dot naught over gamma times 1 minus e to the minus gamma t. By the way, if I did this for y, I would get y is the same formula, just changing the letters, is equal to y naught plus y naught dot over gamma. Hopefully that's still on the screen. 1 minus e to the minus gamma times t. So if I look at just one of the x or y equations, this is for position as a function of time, I can just do a little deduction on this and see what this kind of looks like. I can say, well, look, at t equals 0, this term goes away because at t equals 0, it's just 1 minus 1 is 0. I get x equals x naught. That's what we expect at t equals 0, right? And then I can say, as t approaches infinity, right? Now this term goes to 0, and I get x approaches x naught plus x naught dot over gamma. And so if you were to draw a graph of like time and position here, like this, and call this your x naught, this is where it starts, right? If your x naught dot is positive and gamma is positive, it's going to look something like this. It's 1 minus a decaying exponential function, and so instead of the decaying exponential function going like this, it goes like this because it's 1 minus, and it's asymptotically approaching a position up here, and this position up here is this is x naught dot over gamma, and so this whole height is x naught plus x naught dot over gamma. And that's the, for large t. That's how far your object travels. It doesn't travel infinitely far when it's got linear air resistance in it. It comes to a stop, and this is how far the total distance it travels. It'd be the same thing for y, of course, so I won't do the y's. They'll look exactly the same thing. That's your position as a function of time for an object under linear air resistance in your x direction motion. So if we do the same thing in the z direction now, as opposed to the x and y, we get something slightly different because gravity is acting in the z direction. This is the equation we got for the velocity as a function of time for the z direction with gravity acting. And we're going to rearrange this slightly. We're going to gather up the two terms that have the exponent multiplying them, and so I'm going to rewrite this as z dot naught plus g over gamma e to the minus gamma t. That's these two guys, and then minus g over gamma, like that. And so then I can start to integrate this piece, and I can say, well, dz dt is equal to that, is equal to z dot naught plus g over gamma. Again, these are just constants, right, that are multiplying e to the minus gamma t minus g over gamma. And so I can say dz is equal to this thing, z dot naught plus g over gamma times e to the minus gamma t minus g over gamma, that should be a square bracket, times dt. Now I've separated variables and I can integrate, right? And this isn't too hard to integrate. I can break up this one into two integrals. This goes outside the integral because that's the only piece with time dependence, and that's an additive term. And so I can say, look, the integral from z naught to z of dz is equal to z dot naught plus g over gamma times the integral from 0 to t of e to the minus gamma t. That's an easy one, right, dt. And then I can say minus g over gamma times the integral from 0 to t of dt. Both of those integrals are pretty easy. This is z minus z naught for this guy, right? I'm sorry about the reflection there, about that. Is equal to, so z dot naught plus g over gamma, that's my multiplicative term out front. And this is the evaluation from 0 to t of e to the minus gamma t over minus gamma. That's what that integrates to. And this is minus g over gamma times t. I don't think I have room to work all that out, but maybe I do. And so when I integrate this, evaluate this at t and 0, I get this is z minus z naught is equal to z dot naught plus g over gamma times, so it's this evaluate t, so it's e to the minus gamma t over minus gamma. And then minus the evaluation of that is 0, so it's minus 1 over minus gamma. That t should be in the numerator, sorry. Minus g over gamma times t. I have a little room left at the bottom, so maybe I can make all this work out. This gives me, so I'm going to, I'll show you what I'm going to do here. So I'm going to say z minus z naught. How about if I move the z to the other side, the z naught to the other side? So z equals z naught plus, because that's the way I usually have my final position defined. So this quantity, z dot naught plus g over gamma, right? Times, okay, so let's look at this bracket thing. This bracket thing has a bunch of minus signs in it. So I'm going to pull a 1 over gamma out in front, 1 over gamma, right? That's the gamma out there. And this just becomes 1 minus e to the minus gamma t times minus g over gamma times time. So I just pulled a 1 over gamma out, and this is a plus sign, and this is a minus sign, and so I put this guy first as a 1 because his 1 over gamma is out here, and then this guy's a minus, and so I get this 1 minus e to the minus gamma t like I've been getting in a few places before. And so right away you can see at t equals 0, I get this piece goes away, and this piece goes away, and I get z equals z naught at t equals 0. Right? And as t goes to infinity, I just get this multiplicative term about how far it travels based on this piece, and then now it's going at a constant velocity. That's its terminal velocity. I guess we can look at that again in a second, times the time. And so we talked about this kind of already. And so in the downward direction. And so this gives me what I expect to get. Maybe I'll just erase the page and write it a little cleaner here. Let me just write it up here. Right. And so I might write it this way: z equals z naught times, so this piece, so plus, so I'd have a 1 over gamma. Maybe I can just write it this way. How about this? Z dot naught over gamma plus g over gamma squared. I just absorbed this gamma into this guy, right? I don't know if that's the best way to do it. 1 minus e to the minus gamma t minus g over gamma times t. And so now we have the x, the y, and the z positions as a function of time for an object that's moving as a projectile under linear drag. So, and we can look at a few examples, like this is projectile motion with linear air resistance. This is the vertical motion. We've already derived this equation for the velocity. And so we can say, at what time t is the projectile at its maximum altitude. In other words, we send the object up with initial velocity z naught, it goes up and it comes back down, right? And so up here, z dot is equal to 0, and so we can just set that here, right? We can set this equal to 0, and then solve for t, right? With just from here over, solve for t, and so we can rearrange that, and we can get z dot naught plus g over gamma e to the minus gamma t is equal to g over gamma, right? I've just added this to the other side. And now I'm going to try to isolate the time, and I'm going to do it by getting a positive exponent on it. So I'm going to multiply it over to this side. And so I'm going to cancel it here, and this is going to be e to the plus gamma t, right? If I multiply both sides by e to the gamma t, then I can divide this guy back out, and I get gamma over g, multiply both sides by gamma over g, z dot naught plus g over gamma is equal to e to the gamma t. I can multiply that through, and this becomes z dot naught gamma over g plus 1. When I multiply this guy through, equals e to the gamma t. And so I take the log of both sides, and so that gives me gamma t is equal to the log of z dot naught gamma over g plus 1, or t is equal to 1 over gamma log of z dot naught gamma over g plus 1. So if I want to figure out the height, this is the time we just determined, the time to max height. This is the height as a function of position. And so this is the position. The vertical height is a function of time, right? And so if I want to know what the vertical height is at this time, I just take this time here and plug it in for the times here and here, right? And so I can get z is equal to z naught. This won't look too pretty, plus z naught dot over gamma plus g over gamma squared. That's this term times, and so this one will simplify a little bit. It's 1 minus e to the minus gamma times the time, which is this thing in parentheses. And so I'm going to write as 1 over gamma log of z dot naught gamma over g plus 1. Right? I just took this piece in and stuck it in for the time, e to the minus gamma, and so I close this parentheses minus, and so now I have g over gamma times that thing in parentheses there, which is 1 over gamma log of z dot naught gamma over g plus 1, and that gives me z naught plus z naught dot over gamma plus g over gamma squared. Now let's deal with what's in here. So this gamma cancels this gamma, and then I have an e to the minus log, and so that's just 1 over this thing in parentheses here, and so it's equal to minus 1 over z naught dot gamma over g plus 1, like that, because the gammas cancel and the minus 1 can be made into an exponent for the argument of the logarithm, and then the logarithm of and the exponent cancel, and so it just becomes 1 over that term minus g over gamma times, so I'll say minus g over gamma squared log of z dot naught gamma over g plus 1. It's not super complicated. I don't know if we can do any further simplification on this. This doesn't simplify too much, just a little bit, plus I could probably do a little more if I worked on this a little bit, over gamma plus g over gamma squared times, and so this becomes, I'm going to cross multiply and use a common denominator. So this is z naught dot gamma over g plus 1 minus 1 over z naught dot gamma over g plus 1 minus g over gamma squared times the log term, z dot gamma over g plus 1. You can just wrestle with this math a little bit if you want. You notice these two guys cancel. And then I can multiply the top and bottom of this fraction by g, and I can get it, that would give me a g over here. And so if I wanted to write it just up here, without a lot of fanfare, I'll pause this thing and see if I can get a simpler version of this. So these would simplify to my z, my final position. This is at the top at max height, right? So what I did was I took the position, I substituted in the time for maximum height into here, and I'm just simplifying a little bit, and I don't care when you stop. But this is z naught plus z naught dot over gamma plus g over gamma squared times, and so this is just z naught dot gamma over, because the plus 1 and the minus 1 canceled each other, and I multiply the top and bottom by g to get rid of that. This is z naught dot gamma plus g. I don't see a quick simplification over there, minus g over gamma squared times the log of z dot gamma over g plus 1. So we can look at a projectile in 2 dimensions. We can have a horizontal and a vertical dimension, and these were the expressions we derived. Technically, there should be an x naught here. X equals x naught plus. We're probably going to set the x naught and the z naught equal to 0 and just say the projectile starts. So we'll pick x naught equals 0 and z naught equals 0. So just to eliminate the length of equations, this is the equation for our x motion, and this is our equation for our z motion. And what we're going to do is we're going to solve this expression for t, and then substitute in here so that we'll have z as a function of x. And then that gives us the shape of the curve, but we can also do things like determine the range and things like that. So I'm going to start with this equation. I'm just going to solve for t. First, I'm going to set x equal to 0, x naught equal to 0, right? And so if I multiply, if I solve, I'm going to take this term to the left-hand side. I'm going to get gamma x over x naught dot is equal to 1 minus e to the minus gamma t. Right? So what I did here, let me clean that up just a little bit. I have a dot there, right? I just set x naught equal to 0, multiplied by gamma divided by x naught dot, and that left me with this on the right-hand side. And then I can say e to the minus gamma t is equal to 1 minus gamma x over x naught dot, right? I add that and subtract that. And then I can take the log of both sides, and I can say minus gamma t is equal to the natural log of 1 minus gamma x over x naught dot, like that. And so that means that t is equal to minus 1 over gamma log of 1 minus gamma x over x naught dot, like that. This piece I can substitute into here, and that'll give me z as a function of x. And so I'm going to write that out. Again, I'm going to pick z naught equal to 0, so this is going to give me z is equal to z naught dot over gamma plus g over gamma squared times 1 minus e to the minus gamma times this thing, minus 1 over gamma log of 1 minus gamma x over x naught dot. Right, the thing in square brackets is just my t from up here. And I'm going to close that parentheses, and I'm going to say minus g over gamma times this thing again, minus 1 over gamma log of 1 minus gamma x over x naught dot, close parentheses, like that. Now I have my z as a function of x. You can see this is going to simplify a little bit. For example, I'll put out a different color here. This minus gamma here and the minus 1 over gamma here are going to multiply to 1, and then the log and the e are going to cancel out. And so this equation is going to become z equals z naught dot over gamma plus g over gamma squared times, and so this is going to be 1 minus parentheses 1 minus gamma x over x naught dot. It's getting harder and harder for me to get my dot in there. Let me try that just differently. X naught dot, something like that. It's not much better. Because the minus gamma and the minus 1 over gamma canceled, and the log and the exponent canceled, so it's minus 1, minus parentheses 1 minus that, minus, and so I'm going to pull this out, so it's going to be a plus g over gamma squared. That's combining this one and that one, times the log of 1 minus gamma x over x naught dot, close parentheses, like that. And if I do one more line here, I get z naught dot over gamma plus g over gamma squared times, so it's 1 minus, so this just becomes gamma x over x naught dot, right? Because the ones go away, and the minus becomes a plus, plus g over gamma squared log of 1 minus gamma x over x naught dot, like that. That gets my z in terms of my x. Back when we did this without air resistance, this was clearly a quadratic parabolic formula. It's clearly not here, right? It's more complicated than that. So let me pause here for a second. So I've rewritten the equation for z as a function of x, and now I'm going to say so the object does this, right? And I'm going to look for this spot where it comes to 0. So I'm just going to set z equals 0 and see what I get, right? And so this gives me 0 is equal to z naught dot over gamma plus g over gamma squared times gamma x over x naught dot plus g over gamma squared log of 1 minus gamma x over x naught dot. Like that. That's when it's hit the ground, z equals 0. So it's difficult to solve this expression for x, and so what we do is we expand the log of 1 minus gamma x over x naught dot the following way. Log of 1 minus u, I don't expect you to know this, is minus u squared over 2 minus u cubed over 3 minus, and so on. Here u is equal to gamma x over x naught dot. And so we can substitute this in for this, and even if we just keep the first two terms, this is equal to minus, and so I'm going to have gamma x over x naught dot minus gamma squared x squared over x naught dot squared with 2 out front of it like this, minus dot dot dot, right, like that. And we'll just keep the first two terms. And so we're going to take these two guys, and we're going to stick them in for the log there. Right. And so we get 0 is equal to z naught dot over gamma plus g over gamma squared times gamma x over x naught dot plus g over gamma squared times, so what's in these parentheses here is minus gamma x over x naught dot minus gamma squared x squared over 2 x naught dot squared, like that. This might be a little easier to simplify. So I've erased it just to give me some space. And so all I did was I kept the first two terms in the log expansion. I'll go back and I'll keep 3 in a second, but I just want to show you what happens when we just keep 2. And so this equation becomes this. Again, this is at x equals x max, right? We set z equal to 0. Z was on the left-hand side. And we set z equal to 0, and that gets us to the x position where z is 0. And so hopefully you can see that this is gamma g over gamma squared times gamma x over x naught dot, and this is minus g over gamma squared times gamma x over x naught dot. So this term here cancels with that term there. Hopefully you can see that, right? And so what this leaves me with, I'm going to write back up here, is 0 is equal to z naught dot over gamma times this piece here, which is gamma x over x naught dot this term doesn't count, so it's just that times that, and it's plus this one times this one, and so it's minus g over gamma squared, right? And then times this guy, which is, I got the minus sign taken care of. I've got a gamma squared x squared over 2 x naught dot, right, like that. And I'm going to cancel some things out, right? This gamma cancels with that gamma. This gamma squared cancels with that gamma squared. I have, this x naught dot should be squared. And so this x naught dot cancels with one of those, so that's no longer squared. One of these x's cancels with one of those x's. And so what I get here is I get 0 is equal to z naught dot minus gx over 2 x naught dot. That's pretty simple, but we just kept two terms in our expansion, right? And so we don't even have any gamma dependence in here anymore. And if I solve this for x, I get x is equal to 2 x naught dot z naught dot over g. And if you remember, x naught dot is just the x component. This is our v naught, right? This is just, if that's my angle theta, this is my x naught dot, right? It's the thing we called v sub x naught. And this is my z naught dot. This is equal to v naught sine theta. And this is equal to v naught cosine theta. And so this simplifies to, or is equal to 2 v naught cosine theta times v naught sine theta over g. And this is equal to v naught squared sine of 2 theta over g. And if you remember, that's the range equation for a free projectile. So if we only keep two terms, we get back the range equation from the undamped, from the no air resistance case. So now I'm going to take you back here for a second, and I'm going to put a third term in here. All right, and we're going to see what that looks like. So we're going to substitute in for this log of 1 minus u, or this log term, so that we can solve. But this time we're not just going to keep two terms, we're going to keep 3 terms. And so it'll come out a little different. When we kept 2 terms, we saw just the projectile motion without air resistance. The expansion of this, which you can look up, I'm not going to do for you, is minus u squared over 2 and minus u cubed over 3 and so on. And so we're just going to keep all 3 of those. And so that means we're going to use u equals gamma x over x naught dot and substitute this in for that log term, and we'll see how it comes out. And so we get u is equal to 0 is equal to, and so z naught dot, this doesn't change, over gamma plus g over gamma squared times this gamma x over x naught dot term plus g over gamma squared times, and so now I'm going to substitute in this guys with that for u in here, and so I'm going to put square brackets here. I'm going to have a minus u, so it's minus gamma x over x naught dot, right, minus gamma squared x squared over x naught dot squared times 2, because I've got a 2 there, and then I have a minus gamma cubed x cubed over x naught dot cubed with a 3 there, and there will be additional terms. We're going to drop all those terms. You can see that, by the way, that if I pick a small, I can pick a sufficiently small value of gamma, regardless of the other parameters, that successive terms beyond a certain point will be negligibly small if I go for smaller and smaller damping, right? And so because that's a gamma and a gamma squared and a gamma cubed and so on. So I could eventually make the terms not matter. So we're going to say this term matters. How does that change things? And right away, just like before, we noticed that this term here, when combined with this one, is going to cancel with this term. And so those two right off the bat will go away. And so I'm going to write the terms we get after that. We get 0 is equal to So in this term, the gammas are going to cancel, and I get z naught dot x over x naught dot. Remember, the 0 here is because this was actually an equation for z, and we're trying to find the maximum value of x, and so this is a projectile motion problem, and so I have an x position here and an x position here, and so when z equals 0 at the ends, one of them is going to give me the initial starting position for x, which we set to 0 actually back there, and then this will give me the maximum value of that x has when z is 0, so when it's back on the ground. So we're looking for the range in this problem, and we did it for no air resistance by keeping 2 terms. Now we're keeping 3 terms. And so now I've multiplied this guy by this guy, canceled the gammas, and that takes care of this term. And then I'm going to get g over gamma squared for this guy, and he's going to be multiplied by minus gamma squared x squared over 2x naught dot squared minus gamma cubed x cubed over 3x naught dot cubed and then I'm just going to multiply that out, and this is going to give me a z naught dot x over x naught dot, and then I'm going to get, so the gamma squared is going to cancel in this guy, and I'm going to get a minus. Let me clean that up just a little bit. Z naught dot times x over x naught dot, and then I'm going to cancel those gamma squares on this term, and I'm going to get minus g x squared over 2x naught dot squared, like that. That's what this multiplied by that gives me. Right. And then I'm going to get a minus, so the gamma squared is going to cancel 2 of those gammas, and I'm going to get a minus g gamma x cubed over 3x naught dot cubed, like that. And so I'll rewrite this one down here. I get 0 is equal to z naught dot x over x naught dot minus g x squared over 2x naught dot squared minus g gamma x cubed over 3x naught dot cubed. And you'll notice a few things. This is, first of all, I can cancel an x naught dot out of each denominator, assuming my initial x velocity isn't 0. If my x velocity is 0, it's not an interesting problem, because I'm looking for the maximum value that x gets to. And if it's got no x velocity, it doesn't go anywhere. So I can cancel that and make that a 1. I can cancel that and make that a 2. Right? I just multiplied everybody by x naught in the numerator, x naught dot. Similarly, I can cancel an x and an x and an x like that. And this gives me that 0 is equal to, so z naught dot minus gx over 2x naught dot minus g gamma x squared over 3x naught dot squared. Hopefully I did all those right. So you can see this is a quadratic equation in x, right? And so it's going to give me 2 solutions. It's going to give me this solution, which I expect, and this solution, which I expect, right? And so I'm going to multiply everybody by the inverse of the coefficient of the x squared, and so I get the x squared by itself over here, so it looks like a quadratic. And so then this is going to be plus, I'm going to have minus 3x naught dot squared over g gamma. It's the inverse of the coefficient for the x squared multiplying this guy. I'm going to multiply everybody by that by minus gx over 2x naught dot, right? Same thing with this guy, plus minus 3x naught dot squared over g gamma times z naught, right? And if I'm equals 0, right? This is a quadratic formula that I'm going to solve. This is a quadratic equation I'm going to solve. And so let me come back up to here. Right. And I get if I fill that out, I get an x squared, and so this simplifies to plus 3x naught dot over 2 gamma x. So you can sort of see one of these x's cancels with one of those. The g cancels with the g. The two negatives become a positive, and I get a 2 gamma denominator and a 3x naught dot in the numerator. And then I get a plus or a minus. This guy just stays more or less the same. Minus 3x naught dot squared over g gamma z naught dot equals 0. And I'm going to solve this using the quadratic formula. So I'm going to say, I'm going to have the standard formula is x equals, if you have ax squared plus bx plus c, you get x equals negative b equals 0. Plus or minus the square root of b squared minus 4ac all over 2a. So in our case, I get x equals negative, so it's this thing, it's 3x naught dot over 2 gamma plus or minus the square root of, so it's this mess. It's b squared, which is 3x naught dot over 2 gamma squared minus 4 times 1, because my coefficient for x squared is 1, times this mess here, which is 3x naught dot squared z naught dot over g gamma. So it's negative b plus or minus the square root of b squared minus 4 times the coefficient of the x squared times the leftmost guy. Ooh, I left a minus sign off of there. There we go. All over 2. All right, and so that gives me x equals negative 3x naught dot over 2 gamma plus or minus the square root of, and so this is 9x naught dot squared over 4 gamma squared plus 12x naught dot squared over g gamma times z naught dot. All over 2. So we're going to factor, if you notice this is a perfect square, obviously, we're going to factor this out of the square root, and we're going to we're going to move the denominator. And so I'm going to rewrite this way. I'm going to say this is x equals, so minus 3 x dot naught over 4 gamma, sorry, just gamma. I'm going to try to square. That's combining the 2 over here. I have a plus or minus. I'm going to pull the square root, the square root of this guy out. So I'm going to say this is 3x naught dot over 2 gamma. And then I'm going to put this 2 in there. And so I'm going to have 2 times 2 gamma. It's going to end up being a 4 times the square root of what's inside. I have to be a little careful how I do this. So this is just going to be 1. That way, if I multiply this guy back in the radical, when it comes inside the radical, it gets squared, and it'll give us that number back. Plus, and so now what's inside, I have to multiply by the inverse of that. So if I carried this through, I have to have 4 gamma squared over 9 x naught squared, x naught dot squared. The inverse of this thing, so that when I multiply this thing through the radical which I pulled out, it'll make that 1 without that 2 there, right? And so the 2 comes from the denominator, and that multiplies everybody from the outside anyway. And so I get a 12 x naught dot squared. That's this piece over g gamma. And then z naught dot like that, right? And so I can cancel some terms here, maybe. If I can find a marker. Here we go. Right. I can cancel an x squared and an x naught dot squared and an x naught dot squared and a gamma and a gamma. And then I can take a 9 and turn it into a 3, and that turns the 12 into a 4. Right, and I think that's all I get out of that. And so this becomes x equals minus 3 x naught dot over 4 gamma plus or minus 3 x naught dot over 4 gamma times the square root of 1 plus, and so it's 16 gamma, that's what's left on top, over 3g z naught dot. And so this is actually a simplifiable thing. Since gamma is small, I can make this, by choosing gamma small enough, I can make this term small relative to this term, and I can use a binomial expansion on this piece and get a algebraically simple form that I can manipulate. Also, I'm going to use the plus because all these terms are positive. My initial velocity is positive, my gammas are positive, and I want the x max. It's what I want. I want the largest value of x. I want it, remember, we're calculating the position of the end of the trajectory, right, the range. And so x max is over here, and so I want the big one, so I'm choosing the positive root. And so I have to do an expansion on this guy. And if you remember, if you remember 1 plus alpha to the n is 1 plus n alpha plus dot dot dot. And so this expression here becomes x equals minus 3 x naught dot over 4 gamma plus 3 x naught dot over 4 gamma times 1 plus 1/2 times 16 gamma over 3g z naught dot. And so I get x is equal to minus 3 x naught dot over 4 gamma plus 3 x naught dot over 4 gamma plus 8 if you remember the binomial expansion, you can do 1 plus alpha to the n is equal to so we can use the term, the binomial expansion to get an approximate value for the term in the radical using 1 plus alpha to the n is equal to 1 plus n alpha plus n times n minus 1 over 2 factorial alpha squared plus dot, dot, dot. And so the alpha here will be this piece, right? And we'll have to do just a little bit of work with that. So we're going to come up to the top, and we're going to write x is equal to minus 3 x naught dot over 4 gamma plus, again, we're taking the positive root because we want x max. We want that if our projectile looks like this, we want this position, not this position. And so this is going to be 3 x naught dot over 4 gamma times, and now instead of multiplying by this piece, we're going to have this piece in there. If we're representing this radical with a binomial expansion, here we're going to have alpha. The thing that's alpha in here is 16 gamma over 3g. That's what our z naught dot. And n is equal to 1/2. That's the exponent on this thing, right? And so this is times 1 plus n, which is 1/2. So it's 1/2 times the thing I'm calling alpha, which is 16 gamma z naught dot over 3g. Right, that's this piece, plus, so 1/2 times 1/2 minus 1, which is minus 1/2, divided by 2 is minus 1/8, right, so minus 1/8 times alpha squared, so this is 16 gamma z naught dot over 3g squared. That should take care of all of it, right? And that's this guy. So you can probably see that this term and this term is going to cancel after it multiplies out. And so we'll just be left with 2 terms. And you can simplify the algebra, but I'll just write it out for you. We get x is equal to 2 x naught dot z naught dot over g minus 8 x naught dot z naught dot squared over 3 g squared gamma. And there would be plus higher order terms.